Hi, I'm Tim Tyler, and today I will be addressing the question of how long before superintelligence. Firstly, to explain the terminology, a superintelligence is an agent which is vastly smarter than a human in most domains. Perhaps the nearest thing we have to superintelligence today are companies. A company can possess intelligence which exceeds that of an individual human in many domains. However, companies don't really qualify as superintelligent agents because they're not smart enough across a range of different problems. Companies may attain superhuman performance in some areas and yet exhibit relatively poor performance in other ones. Often a company is only as smart as its smartest employee. For example, consider the case of ability at the game of Go. A company may be able to play Go better than its best employee, but it will probably not be a superintelligent Go player simply because there is no known effective algorithm for parallelizing the problem of playing Go and distributing it across multiple employees. This issue can be illustrated by a diagram. A company usually consists of a network of individual human brains. There are communication bottlenecks between the brains, and algorithms must split a problem into modular chunks in order to run efficiently over such a network. A genuine superintelligence would probably not have that architecture. It would dispense with the communications bottlenecks between the nodes, and thus be able to handle larger problems without requiring that they first be divided up. If we do not have superintelligence today, when will it arrive? I'll argue that superintelligence will come soon after synthetic intelligence reaches human performance levels. Once human-level synthetic intelligence is attained, machines will be able to contribute extensively to the research and development needed to produce the next generation of intelligent machines, thus accelerating their development. Also, by the time we have human-level machine intelligence, progress is likely to be taking place rapidly, simply on the grounds that technological development is constantly accelerating. So, the next question is, when will we get broadly human-level performance from intelligent machines? One way in which this question has traditionally been addressed is by looking at the hardware requirements for something with broadly equivalent functionality to the human brain. Hans Moravec produced one of the first estimates of when this might happen way back in the 1980s. He looked at the computational properties of cells in the retina performing edge detection and motion detection and compared these to some electronic signal processing equipment which he considered to perform a similar function. He came up with some MIPS per neuron figures and then extrapolated from these to produce an estimate representing the computational power of an entire human brain. Other teams have subsequently analysed other mental subsystems, including parts of the auditory cortex and the cerebellum, and come up with broadly comparable figures. Plotting these on a graph with the computational power of existing computers suggests that human-level computing hardware will become available in supercomputers around 2010 and will become available in desktops around 2020. However, according to most researchers in the field, hardware is not the limiting factor. We do not know how to utilise the hardware we currently have, let alone what will be available in 2020. It is common for computer software to lag behind the capabilities of its associated hardware. The effect will be familiar to anyone who has owned a computer games console near the time of its launch. Software contains the complex parts of the system, and it is those which are difficult to create and maintain. So, hardware estimates provide a lower bound for when we will have superintelligence, but are not the whole story. Are there estimates of how difficult it would be to create the required software? Ray Kurzweil has attempted such an estimate, arguing that the design of the human brain is of a manageable size since it is stored in the human genome. Here he is at Stanford in 2006 presenting his case.
Now, a key point about the complexity of the brain, and this is really a very key point, because one of the objections is, the brain is too complex. I mean, there's 100 trillion neurons and 100 billion neurons, 1,000 connections per neuron, 1,000 ion channels per connection. It's all these many nonlinearities. This is a level of complexity that's just way beyond today's technology. That is the apparent complexity if you look at a mature brain. But the design of the brain is a billion times simpler than that. How do we know that? Well, the design of the brain is in the genome. The genome has the design of the human body and brain. And it's 800 million bytes, but it's replete with redundancies. One sequence, ALU, is repeated 300,000 times. I've shown in the book how you can compress, using lossless compression, the genome down to 30 to 100 million bytes. So the genome, which describes the design of the body and brain, has 30 to 100 million bytes, which is less than Microsoft Word. And it's not, my point is not that it's a simple system, but it's a level of complexity that we can handle.
However, Ray Kurzweil's argument was subsequently criticized by Douglas Hofstadter later at the same event. Here's Hofstadter putting his case.
Ray suggests that maybe our brains have only 10 to the 8 bytes worth of information in their structure because of the genome. Well, maybe, but what if it is really something like 10 to the 8th button pushes on a jukebox, where when you push the button on the jukebox you get a record out, and the record actually contains an unbelievable amount of information.
So, who is right? Does the brain's design fit into the genome or not? The detailed form of proteins arises from a combination of the nucleotide sequence that specifies them, the cytoplasmic environment in which gene expression takes place, and the laws of physics. We can safely ignore the contribution of cytoplasmic inheritance, however the contribution of the laws of physics is harder to discount. At first sight it may seem simply absurd to argue that the laws of physics contain design information relating to the construction of the human brain. However, there is a well-established mechanism by which physical law may allow just that, an idea known as the anthropic principle. This argues that the universe we observe must necessarily permit the emergence of intelligent life forms. If that involves the coding of the design of their brains into the laws of physics, then so be it. There are plenty of apparently arbitrary constants in physics where such information could conceivably be encoded, the fine structure constant, the cosmological constant, Planck's constant, and so on. At the moment it is not even possible to bound the quantity of brain design information which could be so encoded. When we get machine intelligence we will have an independent estimate of the complexity of the design required to produce an intelligent agent. Alternatively, when we know what the laws of physics are, we may be able to bound the quantity of information encoded by them. However, today neither option is available to us. Anyway, even if Kurzweil was right and the design of the human brain fits onto a CD-ROM, then that would still represent an utterly enormous search space which would easily take far longer than the entire history of the universe to exhaustively search. So this approach doesn't really permit us to say anything useful about how difficult the problem is. What about the idea that the human brain evolved over the last 600 million years in the time since the Cambrian explosion? Doesn't that give us a clue about how hard the problem is? If we can apply a fudge factor to account for the advantage of engineering design over blind mutations, and another fudge factor to account for the fact that we can crib from nature's solution to the problem, doesn't that help us estimate the level of difficulty involved? Unfortunately no. The anthropic principle again blocks this kind of approach. We have no idea whether our brain evolved via a series of lucky flukes, so we don't know if our own evolution was typical or not. For example, if we imagine a constraint that says that a big meteorite destroys all multicellular life every 700 million years, then the evolution of intelligent life had better take place within that timescale, no matter how many apparently improbable events that involves. How about reverse engineering the human brain? If we can estimate how hard that problem is, won't it at least give us an upper bound on how difficult the overall problem of machine intelligence is? Yes, but reverse engineering the human brain looks pretty difficult, and the task might well take us into the second half of this century. So, while such an approach does, in principle, allow us to bound the difficulty of the problem, the resulting bound is not very tight. We will probably have machine intelligence long before such products get very far off the ground. So, what does all that leave us with? It mostly leaves us with intelligence testing. We can test the intelligence of humans, and we can test the intelligence of machines, and then we can plot the increase of machine intelligence over time and see when it reaches human level. I think this is the most promising approach to estimating when we will first have access to superintelligent machines on other grounds besides sheer hardware capability. So, what intelligence tests exist where we already have access to historical data about machine intelligence? One such area is computer chess. Before Deep Blue beat Kasparov, it was possible to look at the history of chess computer ratings and plot a graph that showed when computers would be able to beat the best humans. That illustrates the potential of the technique, but it also highlights one of its limitations. Any individual test may crap out before human-level intelligence is reached, and fall to a machine intelligence that specialises in solving that particular test. The most obvious solution is to use multiple tests from a variety of different domains. Strategy games, robot control, compression, speech recognition, language translation, IQ tests, and so on. One of the best tests we currently have is the game of Go, a classical oriental board game. Playing Go exercises pattern recognition circuitry in the human visual cortex, which represents a substantial proportion of the human brain by volume. It is a taxing game for both humans and machines. Also, there's a rating scale whose uniformity and linearity is backed up by a handicap system, and there is a long history of computer players and tournaments. Currently, the best computer Go programs rate at around 1 or 2Q, on a scale that goes from beginners at 30Q down to 1Q, and then from 1 down up to 9 down, which represents world champion level. As an intelligence test, Go may crap out before broad human-level intelligence is reached, but to me it looks as though it may well take us to within spitting distance of the target. Go is probably the single best way of measuring intelligence for which we have a good history of machine intelligence in which to ground extrapolations. A 1997 survey of Go programmers produced a wide range of answers to the question of when a program would become world champion. Even with Go, where we have some of the best available evidence, the situation is not yet clear-cut. To finish this talk, I'd like to present a slide which illustrates my estimate of when we will obtain superintelligent machines. The curve is a probability density function illustrating the probability of superintelligence first arising on the specified date. It's a roughly bell-shaped curve peaking around 2025 with a fairly substantial spread indicating my estimate of my level of uncertainty about the issue. Enjoy!